how a computer actually works from the inside. Computer organization and architecture is the study of how different parts of a computer system are designed, connected, and how they function together. Computer architecture focuses on what the system does, such as instruction sets and functionality. Computer organization focuses on how it is implemented, like circuits, connections, and hardware structure. In simple words, architecture is the design, and organization is the implementation. Slight pause. Now let's look at how computers evolved over time. Computers have developed through 5 generations. The first generation used vacuum tubes. These machines were very large, slow, and consumed a lot of power. The second generation introduced transistors, which made computers smaller, faster, and more reliable. The third generation used integrated circuits, further improving efficiency and reducing size. The fourth generation brought microprocessors, which led to personal computers and modern systems. And today, the fifth generation focuses on artificial intelligence and advanced computing technologies. Pause. Transition tone. Now let's understand the basic structure of a computer system. A computer consists of 3 main components: the CPU, the memory unit, and input-output devices. Input devices like a keyboard or mouse send data into the system. The CPU processes this data. Memory stores both instructions and data, and output devices display the final result. The CPU is often called the brain of the computer because it controls all operations. Slight emphasis. The CPU itself has 3 important components. First, the arithmetic logic unit, or ALU. It performs all calculations like addition, subtraction, and logical operations such as AND and OR. Second, the control unit. It controls the flow of data and instructions inside the computer. Third, registers. These are very small and very fast memory locations used to store temporary data during processing. For example, if you calculate 5 plus 3, the values are first stored in registers, then processed by the ALU and controlled by the control unit. Pause. Now let's talk about registers in more detail. Registers are the fastest memory units inside the CPU. Some important registers include the program counter, which stores the address of the next instruction; the memory address register, which holds the address of the data to be accessed; the memory data register, which stores the actual data being transferred; and the instruction register, which holds the current instruction being executed. You can think of registers like a chef's working table. Everything needed is kept nearby for quick access. Transition tone. Next, we move to the von Neumann architecture, which is the foundation of modern computers. This model consists of a CPU, memory, and input-output devices. The most important concept here is the stored program concept. This means that both instructions and data are stored in the same memory. This design makes computers efficient and flexible in executing programs. Pause. Now, let's understand how different parts of a computer communicate. They communicate through system buses. There are 3 main types of buses. The address bus carries the location of data, the data bus carries the actual data, and the control bus carries signals that manage operations, such as read and write. For example, when you open a file, the address bus finds where the file is stored, the data bus transfers the file, and the control bus manages the process. Slight emphasis. Important topic. Now let's understand one of the most important concepts: the instruction cycle. Every instruction executed by the CPU goes through 3 stages: fetch, decode, and execute. In the fetch stage, the instruction is taken from memory. In the decode stage, the CPU understands what the instruction means. In the execute stage, the operation is performed. For example, if the instruction is to add two numbers, the CPU first fetches the instruction, then decodes it as an addition operation, and finally executes it using the ALU. This cycle repeats continuously while the program runs. Transition. Now let's talk about instruction formats. Instructions can have different formats depending on how many addresses they use. Zero-address instructions use a stack and do not require explicit operands. One-address instructions use an accumulator. Two-address instructions specify both source and destination. Three-address instructions provide maximum flexibility but require more memory. So, as the number of addresses increases, flexibility increases, but complexity also increases. Pause. Finally, let's understand performance. Computer performance depends on three main factors. Response time, which tells how fast a task is completed. Throughput, which tells how many tasks can be completed in a given time. And cum,